Here we are in mid-chapter 7 exercises with numbers 19 through 27. It says simplify each expression. We're dealing with square roots. Oh, here we've got some cube roots and seventh roots, which we need to get out of there. We need perfect sevenths or perfect cubes. All right, so 19, here we have 64. Okay, so the square root of 64, we know that one is 8. That guy gets to come out straight up. Now, x to the 13th, that's not a perfect square. There are 13 x's. Let's write them out here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so we get 1, 2, 3, 4, 5, 6. Oh, we left one. So we get 6 perfect pairs, which, yeah, 13 divided by 2, that's x to the 6th. Each one of these comes out as an x, but one of them has to be left in there as an x. And then we have 5 y's. 1, 2, 3, 4, 5. Each one of these pairs comes out of that square root. That's a perfect square. That's a perfect square. So we get y squared coming out. And 1 is left over. And notice this is really handy to see this as 13 halves. Breaks down into 6 full x's, and then 1 is still in a fractional exponent. Same thing, this is 5 halves as a rational exponent to the 5th power, square root, and that would simplify as a mixed number, 2 full y's, and then we get a 1/2 left over, remainder 1. 5 divided by 2 is 2, remainder 1 in there. All right, number 20. Oh, we should circle our answer there. Yeah, that's the end result. It doesn't even look simplified, does it? It looks a little bit more complicated. All right, square root of 45. Let's break down 45 into 3 and 15. Could have done 5 and 9, but that's 3 times 5, so we get 5 times 3 times 3. And now, oops, we have 10 v's, which if you have 10 v's, you're going to have 5 sets of this. Are we okay with that? And we want squares because we're square rooting. And then t cubed, you'll have a t squared, which is a perfect one, and then 1 left over. So each one of these comes out as a v. Let me see. This guy comes out as a 3. So we get 3 v to the 5th. And then 1 t will come out. T squared, square root of t squared is t. And then we get 5 t. There we go. Number 21. We have, what is that? 5 times 10, 5 times 2. So we get 2 times 5 for the number. And then we get, that would be how many sets of t squareds? 7 of them. So I'm going to write it like this. T to the 7th squared. And so squaring that, we'll just be able to pull out 7 t's, and then v to the 6th is v cubed squared. And so here's a perfect square, comes out as 5 t to the 7th v cubed square root of 2. And the 2 is the only thing that couldn't come out totally. You can also think about this as power 14, square root is half, and that simplifies just to the exponent 7. This one has exponent 6, root 2, and similarly comes down here and is the exponent 3. Notice we did the same thing over here. This is 10 root the second root, so that's 10 halves. That came down to a v to the 5th. T cubed is to the 3 halves. 3 divided by 2 is 1, and then there's 1 remaining in there. All right. Now we're going to switch gears with number 22. We've got to have perfect cubes in order to make this work. So we're going to do this and write this out in really slow motion here. So we have 56 is 2 times 28. And that's 2 times 14. And that's 2 times 7. All right, so we really have the cube root of 2 times 2 times 7 times, now I'm going to write all these x's out so we can see it in really slow motion. 3, 4, 5, 6, 7. And then the 12s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oh, shoot, we're almost running into the other problem. So every set of, oops, I missed a 2 there. There we go. Every set of 3 now is a perfect cube, which means we can pull it out. So we have 3 2's, and then we have, skip to 7, we have 3 x's there, 3 x's there. So that's 2 x's that get to go out. That makes an x squared out front. And we have 1 remaining. And then we have 1, 2, 3, 4 sets of y cubed. So cube root that, and each one of these comes out as a single y. 1, 2, 3, 4, 4 of them. So then we're left with the cube root of 7x. So notice if we did this with fractions, this is 7 divided by 3. 7 divided by 3 is 2, remainder 1. There's our 2 full x's, and there's our still 1 remaining under the cube root. If we did this one, this is 12, y to the power 12, root 3, so the exponent is 12 thirds. 12 thirds simplifies simply to y to the 4th power. So there we have it. All right, number 23. All right, cube root of 135, m to the 5th, y to the 24th. Let me see, that is, I don't know, what is that? 5 definitely goes into it. 5 goes into that. Looks like 27 times. If you can identify that and see, hey, 27 is a perfect cube, then that's great. You can leave it like that. But we're going to keep going. 3 times 9, 3 times 3. So we have 5 times 3 times 3 times 3. And this guy, notice if we did it not quite as slow motion, but wrote it out, all sets of 3, we can write like that, m cubed, and then we have 2 left over. And on this one, we could have y cubed. We could get a full another one and another one. That's 9, 12, and we have 2 left over. So every set of 3 can come out. So this guy comes out, 3. Oh, we forgot the little cube root there. This guy comes out as an m. That one, that one, that one, and that one each come up with a y, so we've got a y to the 4th, and then the cube root of everything that is remaining, 5, m squared, and then we have a y squared left over. And if we did these with rational exponents, it's a beautiful way to see it. This is 5 thirds power, power 5, root 3. 3 goes into 5 once, and remainder 2. And then this one is 14 thirds. This is 3 goes into 14 4 full times. You'll notice we have a y to the 4th and remainder 2. We still have a 2/3 power. All righty, there we go. And number 24. Ooh, the 7th root. We can only pull out perfect sevenths or sets of 7 when we do prime factorization. So you might be able to recognize 128 as a perfect 7th. It'll come out. 7th root of 128 is indeed just the number 2. But let's go ahead and write that out. This is, I don't know, 4 times 32. And that's 4 times 8. That one's 2 times 2. That's 2 times 2. That's 2 times 4. And that's 2 times 2. So we get 2, 2, 3, 4, 5, 6, 7. It's 2 to the 7th power. Let's write it all out here, 7th. And then let's write these in sets of 7 because that's what will allow them to come out. So here we take u to the 7th and u to the 7th. Yeah, indeed, we get 2 sets of them in there. And the y's, let's set those up in sets of 7. Y to the 7th, y to the 7th. Let me see, 7 plus 7 is 14. We can do another one. That's 21. And we have 2 left over. So this comes out to be, that's a set of 7. So that's just the number 2. This comes out as a u. That comes out as a u. So that's u squared. And that comes out as a y, y, y. So that's y to the 3rd power. And then everything else is the remainder. So the 7th root of y squared. Good. And notice if we looked at it as rational exponents instead of as a radical, this would be u to the 14 halves power. That just reduces down to, oh, not 14 halves, 14 sevenths power. That's a 7th root. 14 sevenths reduces just down to u squared. Y to the 23rd sevenths, or 23 sevenths. 7 goes into 23, 3 complete times with 2 remainder. So everything we learned about fractions can help us to make sure that we do these problems clearly and completely. All right, number 25. Ooh, here we have a binomial. So we're going to take 4 times 3 and then that. So we get 4 times 3 is 12 minus 4 times this is 16 square roots of 3. It times the coefficient out here in front. Now we take the 2 square roots of 6 and jump it in. And we get 2 times 3 is 6 square roots of 6. And minus 2 times 4 is 8. Square root of 6 times square root of 3 is square root of 18. Do any of these simplify? That one doesn't, but this one, this is 2 times 9, 3 times 3, so that can come out as 8 times 3 times the square root of 2. Remember that when it's 2 of them together, they come out of a square root as a single 3, so it's 24 square roots of 2. Then I think everything else is the same. 12 minus 16 square roots of 3 plus 6 square roots of 6. Can we combine any of those now, like terms? We cannot. And they're simplified as much as they can. Alrighty. Now let's try number 26. Okay, so jump that in there and there. We get 6 minus 1 times that is 7 square roots of 5. Now jump that guy in there and we get minus 18 square roots of 13. Plus 21 square roots of 65. Does anything simplify? Square root of 5 doesn't, square root of 13 doesn't, and square root of 65 was just 13 times 5. There's no perfect square in there at all, so it's just super distribution. And then the last one, number 28. All right, so 8 times 8 is 64. Then 8 times 2 square roots of 11 would be plus 16 square roots of 11 minus 16 square roots of 11 and minus 4 square roots of square root of 11 times square root of 11 square root of 121. Notice the square root of 121 is 11. And yeah, square root of 11 times square root of 11 is 11. So this is actually minus 44. So we get 64 plus 16 square roots of 11. These two combine to 0 minus 44. The answer is just the number 20. All the square roots went away. That's crazy. That's amazing that they just went away like that. But look at this plus and this minus. Those guys are indeed conjugates, which will bring a whole binomial with the square root out of the irrational world.